All right, so the second talk is going to be given by Paul Morris, and it's on the mathematics of dispatchability revisited asterisk.
Well, the asterisk is not actually in the title. So where is the thing that progresses the slides?
We have a remote? We don't have a remote because that was the other one.
So I can just use this.
Yeah.
Okay. So this is follow-on work from papers at KR 98 and AAAI 98 with Nicola Muscetla and Yanni Samardinos. So the concept of dispatchability originated due to the needs on the remote agent experiment, which was on the NASA Deep Space One mission, where an AI system controlled the spacecraft for several days. There was a need in this mission for efficient execution of temporal plans, and the concept of dispatchability proved to be key for that need. So here's a very simple example of a temporal plan. There are two activities, frying eggs and toasting bread. Now, fried eggs are horrible when they're cold, so you'd really like the bread to be toasted first so that you can eat the eggs as quickly as possible once they're done. So the activities of start and end time points, and then there are temporal constraints between the time points. And in this case, there's just one temporal constraint of 2 minutes. Now, this is sort of the basic idea behind dispatchability. If there was a recipe for making breakfast, it would never say, start toasting the bread at such a time that it would be finished 2 minutes before the eggs are fried. Instead, it would say something like, start frying the eggs, and then 2 minutes later start toasting the bread. So it's more like a program. The paper consists of mathematical definitions and proofs. Instead of presenting those, I'm going to try to give you some of the ideas behind the result in this talk. This is an outline of the talk. I'll first describe STNs, which maybe you're all familiar with. Then I'll define a dispatching execution. I'll use that to define a dispatchable network. Then I'll talk about the relationship between a special type of path called Vee-paths and dispatchability. And finally, I'll present a conjecture concerning temporal uncertainty. Now, this is actually my main motivation for revisiting dispatchability. It turns out there's sort of a deep connection between dispatchability and ways of executing temporal networks. So a simple temporal network, it involves the variables which are time points, generally the start and end of activities, and binary constraints, which are the separation between those time points. The constraints are just simple inequalities on the separation between the time points. They have a graphical representation, and I've shown where they show the lower and upper bound. And there's an alternative representation where you essentially only show upper bounds. Notice that a lower bound can be represented as an upper bound by inverting the time points and negating the bound. So here's that simple example I gave you as an STN. I'm assuming that frying eggs takes 10 minutes and toasting bread takes 6 minutes here. So now I'm going to talk about dispatching execution. So the basic idea of dispatching executions is that they involve local checks of correctness. And we will consider partial executions. So a partial execution that is even a dispatching one may or may not have a continuation. There may not be any continuation. So in more detail, here's the requirement for dispatching partial execution. First of all, you can't execute time points out of order, so you respect direct precedence constraints. The second condition is that if you execute a time point, it must satisfy direct constraints with respect to already executed time points. So in particular, you can't execute B before its inferred release time from an executed time point, and you can't go beyond a certain point if the deadline has not been met for some time point. So that liveness requirement, one way of implementing that is through local propagation of bounds. So the local propagation involves propagation only through direct constraints to neighboring time points. And then you can use those bounds to determine the liveness consideration. So here again is our breakfast STN, and let's see how a dispatching execution would work for that. This is just one possible dispatching execution. So we started the exit time 0, and we did our local propagation to get bounds for ending that. Then there's nothing stopping us from executing the T at time 1. This is still a dispatching execution. Again, we propagate, we get this, and let's say we execute that at time 7 and propagate, but now the lower bound here is bigger than the upper bound here, so you can see that there's no way we can continue this dispatching execution in order to execute E prime in a way that satisfies the requirements. So this is no surprise, since local propagation doesn't calculate the full consequences of a particular decision. Now, the interesting thing, though, is that there are some STNs where, in fact, this does work. So here's an example where it does work. It's the one I alluded to earlier as the more recipe type STN. So suppose we execute E again at time 0, we propagate, we get this we get this propagation. Now these two time points have not been enabled yet, so they can't be executed, so the only thing we can do is execute T at time 2. Again we propagate, and it turns out that we can't execute this yet because then this would meet its deadline. So we can only execute this next, and the only thing remaining is to execute that. So everything worked out fine for this STN. So what is a dispatchable network? Well, the definition is it's dispatchable if every dispatching partial execution can be continued to a complete execution. That is, we never get into trouble. Now, in the KR98 paper, it was shown that every consistent STN can be reformulated as an equivalent dispatchable STN, and in a more efficient version of the algorithm was presented in the AAAI 98 paper. That's fine, but it doesn't really tell us how we recognize an existing dispatchable network. This involved going first to the all pairs network and then removing edges from the all pairs network, so it's sort of lost information about the structure of the original network. So here we have a non-dispatchable network and a dispatchable network. What's the difference between them? One thing you can see is there's a path through the future there, and there's a path through the past there. That's kind of the idea, but it's a little more subtle than that. So now I'm going to talk about Vee-paths and how they relate to dispatchability. So Vee-paths are shortest paths in the distance graph that involve some number of negative nodes followed by some number of non-negative nodes. In either case, it may be 0. So here are some examples of Vee-paths. This is kind of why I call them Vee-paths. So notice that a subpath of a Vee-path is itself a Vee-path. So there's a theorem in the paper which says that a consistent STN is dispatchable if and only if for every path there is a Vee-path. The proof is non-trivial. You can read it in the paper. The paper introduces a new execution sequences formalism to facilitate the proof. So here's the distance graph for the dispatchable example that I showed earlier. If you look through these edges in the clockwise direction, you can see that they're a Vee-path. And if you look at edges in the counterclockwise path, they're also a Vee-path. And then every subpath of those are Vee-paths. So it's easy to see that there's a Vee-path between every pair of time points. So why recognize dispatchability? Well, if the network we have is already dispatchable, it would be nice to notice that so that we don't go through the algorithm to convert it to a dispatchable form. But the reason why I was interested in it is because of the connection to dynamic controllability. So I'm going to look at this conjecture. In general, STM's activities may have uncertain durations. For example, frying eggs might take somewhere between 9 and 10 minutes here. Because of the uncertainty, of course, we can't guarantee finishing toasting bread exactly 2 minutes before. So let's relax that condition to 1 to 3 minutes. Now it turns out that our strategy of starting to toast the bread exactly 2 minutes after we start frying eggs still works in all the situations, notwithstanding the uncertainty. To model this, we would really use a simple temporal network with uncertainty where besides the ordinary requirement edges, you have contingent links like this. Now, any STNU gives rise to a family of ordinary STNs called the projections, where the contingent links take on all of their possible values. So contingencies are observable. And in dynamic controllability, we exploit that observability to have an execution strategy that may depend on observations. The network is called dynamically controllable if such a strategy exists. In 2 years ago at CPAIOR, there was a result that showed that if every projection can be made dispatchable, then an STNU is dynamically controllable. If you look at most of the algorithms for checking dynamic controllability, they may be viewed as trying to make the projections dispatchable by adding edges that create Vee-paths. That's discussed in the paper. So now what I'd like to do is I'd like to see if those results might possibly be extendable beyond STNUs. So in an STNU, the contingent links are assumed to be independent. However, if instead of nature causing the uncertainty, we had some other agent causing the uncertainty, that agent might actually have a simple temporal plan of its own. And now the contingent links are no longer independent. You could have a cross-link, for example. Now, the network I showed you here is not actually dynamically controllable because the uncertainty here is too great compared to the requirement. However, for this network, you can actually use this, observing this, to predict when B is going to occur. And if you do that, you can get a strategy which involves executing D exactly 1 time unit after C, and this automatically satisfies that requirement. If you look at, here I've sort of made a schema which shows you the distance graphs for all of the possible projections for that problem, where in this case projection means a consistent schedule for the observed agent. And if you check, you can see in fact that there are Vee-paths between every pair of edges, every pair of nodes, and in fact also all of the projections are consistent. So that leads us to this conjecture that trying to make the projections dispatchable by ensuring Vee-paths might work as a checking method. However, that may be quite tricky because you can certainly add edges to ensure Vee-paths, but if you're not careful, you might actually make some projection inconsistent. I have not presented an algorithm for this. It's just a conjecture for the future. So in this talk, I've deviated a little bit from what is actually in the paper. So this is a summary of what is in the paper. The paper introduces this formalism of execution sequences. It defines dispatchability. It proves this characterization of dispatchability in terms of Vee-paths, and then it presents that multi-agent uncertainty conjecture in a little more detail. That ends the talk.
Thank you. Questions? Christian?
So the new execution sequences stuff that you introduced in the paper, do you think it will either lead to better algorithms for strong control or dynamic controllability, or at least better understanding of why the current algorithms exist? These are rules.
So my purpose was simply to facilitate proving that characterization. So it turned out that the original definition of dispatchability was in terms of an algorithm, a sort of an idealized execution algorithm, and that was not very suitable for proving mathematical theorems. So I needed to introduce a new formalism to facilitate that. And I think it also breaks down the requirements of dispatchability into more forms. An execution sequence is itself a sort of a special case of an instantiation sequence, and the dispatch sequence is a more specific version of an execution sequence.
Other questions? So the identification, you had to prove the existence of a V-path between all pairs of nodes. And so did you talk about the complexity of doing that, or is it just because it's a proof method that wasn't relevant to what you were doing?
There are no algorithms in the paper, only definitions and proofs.
Okay. So do you have any intuition as to whether the V-path characterization is going to be useful algorithmically?
I'm not sure yet. I don't know how much it would cost, for example, to check whether a network already has V-paths between every pair of nodes. I haven't looked into that.
Other questions? We have plenty of time.
You would think it would be proportional to the kind of propagation you do now.
Yeah. I mean, if you think
I think it would be. It sounds like it would be efficient.
So the existing algorithm to construct a dispatchable network, actually a minimum dispatchable network, it involves an adaptation of Johnston's algorithm, which involves basically just one single Bellman Ford to check consistency, and once you've got that, that gives you a potential function, and then it involves doing a Dechter algorithm from every node to every other node. So it's En plus n squared log n.
Other questions?
So for the case of crosslinks, you could think more generally that an agent is in charge of a set of time points, and so basically is controlling an entire subnetwork.
Indeed, yes.
Yeah, and so this, if you think of the solution space for that subnetwork, it's got corners, right, vertices. And those would correspond to the lowercase and uppercase on a single edge. So could you imagine having a set of rules which would say for each corner point, rules that would be analogous to your lowercase and uppercase rules, or?
So you want some kind of labeled edges?
I'm not sure.
Yeah. So in terms of the possible schedules for the agent, you would want to look at the extreme schedules, but because there are. So it depends on whether each constraint is tight or not. So it's not exactly the same as an STNU, where you can consider the extreme projections where every constraint is active, either in its lowest form or upper form. In general, because of these interactions, some of the constraints might not be active. So I think it would be a more complicated situation.
Final question? All right, thank you. That's where we were. Okay, that one. Yes. Okay, so the last talk in this session is a paper from the journal track, and it's going to be presented by Valentino Santucci.
Thank you. Okay, I'm Valentino Santucci. This paper has been published on IEEE transaction on evolutionary computation, and it mainly consists on an evolutionary algorithm, a new evolutionary algorithm for the permutation Flowshop problem. The permutation Flowshop scheduling consists in a set of jobs that have to be scheduled on a set of machines. The machines are ordered, and we have the processing times of every job on every machine. So the solution is a permutation of the jobs, because we have the constraint that job spacing is not allowed. And the objective function investigated in this case is the total flow time. I mean, the sum of the completion times of every job on every machine. Okay, we would like to apply to this problem the differential evolution algorithm, but that's an issue. The differential evolution algorithm is a numerical optimization algorithm, the state-of-the-art materialistic numerical optimization, but it works with real vectors, and we need something working on permutation representations. So we will show how to transform this algorithm this numerical algorithm in a combinatorial algorithm. Anyway, in this slide I show you the three basic steps of the classical differential evolution. They are to iteratively apply the genetic operators of differential mutation, crossover, and selection. And in literature it is understood that the key operators is the differential mutation that allow to automatically adjust the balance between exploration and exploitation of the algorithm. Here, this is the main scheme of the algorithm. We randomly initialize the population of solutions. We enter a main loop where we do the three genetic operators, and this is the definition of the differential mutation. So we take three random individuals, x0, x1, x2, and we have a parameter, f, is a value between 0 and 1, and we generate a mutant solutions using this formula here. Okay, why we want to apply this algorithm to permutation Flowshop scheduling? Because differential evolution is the state-of-the-art in numerical optimization. Maybe it's the same also in combinatorial optimization. And because we want to exploit an idea on the idea that I show you later of the group structure on the permutation space. Okay, we need some small background of algebra. We need to know what is a group. A group, I think, is the most simple algebraic structure, it is simply a set X with an operation that is closed on this set and that has to have these three properties. It has to be associative, it has to admit neutral element and the inverse elements. Moreover, we have to consider a generating set that is a subset of the group such that every element X of the group can be written as the product of the generators. We can say they are the prime numbers of the set. And that's okay. And we have a nice geometric interpretation of a finitely generated group because we can build a graph. Its name is the Kerry graph. In this graph, the vertices are the elements of the group, while there is an arc for every. So there is an arc from X to X product G, where G is a generator, and this arc has a label, has a color, that is the generator. Okay. This allows us to build a connection between a Kerry graph, thus a group, and a combinatorial search space. We can imagine that the set, the group set, the vertices of the Kerry graph are the whole set of solutions of the combinatorial problems. While we can, in some way, say that the generators are the simple search moves that allow us to move from one solution to the other. I'll show you in the next slide with a simple example what I mean here, but this allows us to induce neighborhood relationships among solutions, to induce a distance function between the solutions, and also to have, very important this point, to have a single representation for both the solutions and the moves in the solution space. Okay, this is a very small example. Consider, for example, the combinatorial problem with bit strings of length n. They satisfy the properties of a group if you consider the bitwise XOR operation. In these cases, the neutral element is the all zero string. The strings are inverse of themselves, and the generators are the strings with exactly 1 bit, and all other are 0. And considering the XOR, they are exactly the bit flip moves. So the Kerry graph is, in this case, the hypercube, and the distance, the shortest path distance in this graph is exactly the classical Hamming distance. Okay, but we're back again to the permutation Flowshop. We know that the solutions are permutations, and we know also that the permutations form a group, the symmetric group, with the usual permutation composition operation. So you can compose two permutations. They are simply discrete bijective functions. And this allows us to build an algebraic differential evolution that simulates in some way the numerical one. So the recipe to build the differential evolution is to redefine in some way that has to be consistent with the classical implementation, the free genetic operators of differential mutation, crossover, and selection. Okay, for crossover, there is no problem. There are a large variety of crossovers for permutation representations. Also for the selection, that's no problem. What we do here is to consistently define a discrete differential mutation. Sorry. Okay, so this one was the question, and we can devise a discrete differential mutation by redefining the free operators, plus, times, and minus. And okay, we can start by the plus and the difference, the sum and the difference. We can simply say that permutation x plus permutation y is equal to x composed y. Okay, and we can say that x minus y is equal to the inverse of y composed x. This is consistent. Sum and difference are consistent to each other, like in the classical arithmetic. So we don't need to consider here the generators, but the generators comes into play when we want to redefine the multiplication operator. Okay. In the case of permutations, we can consider that the generating set based on adjacent swap moves. What I mean, an adjacent swap move is simply an exchange between adjacent items in a permutation, and we can express this move with a permutation. So in this example, we have permutation with 3 elements. The exchange between the first and the second element is this one. It's exactly the identity permutation where I have exchanged the first and the second element. So we have that x composed gi is the permutation x where the items at positions I and I plus 1 have been swapped. Okay. Here we have the definition of the multiplication operator. We have that f is the parameter has to be a real number in 0, 1, and we have that the permutation delta, we suppose that the permutation delta has the shortest decomposition in terms of the generators, the adjacent swap, that has length L. So the truncation is simply to truncate the decomposition after the first F times L generators. Okay. Now we know what we want, but we don't know how to generate the composition of a permutation. So, but it is very easy. We only need to sort the permutation using a bubble sort algorithm. Why we sorted it? Because bubble sort algorithm only do adjacent swaps, and while we sort, we have to annotate the adjacent swap, and then at the end we reverse the sequence of the swap, and we have the decomposition. Anyway, bubble sort is deterministic. It always gives us the same decomposition, so we have generalized it by randomizing it. The randomization of bubble sort, okay, it is theta n square, theta n square algorithm, like the classical bubble sort, and it is correct because it monotonically decreases the number of inversions of the permutations. And so at the end, we have one of the random decomposition of the permutation. This is also usable for generic arrays. Okay, let me give a geometric interpretation of this process. We want to generate U, and we know x0, x1, x2. Suppose x0, x1, x2 are these 3 permutations here. This is the search space, also known as permutaedron, the Kerry graph. Okay. And the arcs have a color depending of the generators, on the generators. And the first operation is to compute the difference, x1 minus x2. This exactly corresponds to one of the shortest paths from x2 to x1. Then suppose that the parameter f is 1/3. we truncate the decomposition, so we remove the one arc, the last one, and at the end we apply this permutation to x0, and we move to the mutant u. Okay, there are also other algorithmic components, but for the sake of time I jump this slide. I'll show you a summary of the results on this permutation flowshop problem. We have applied this algorithm on a standard benchmark suite of 120 instances. We have found the best average results on 95 of them. We have also found best peak performances in 75 of them. And most importantly, we have 14 new best known solutions on some of the biggest problems of the benchmark suite. And we have also applied other experiments to check if the differential mutation is the most important component of our algorithm, and it was. So this is the lowest is better. The other are, for example, this one is a purely random mutation. It's incredibly worse. More details are on the paper. And I bring, some conclusions. We have introduced an algebraic framework for combinatorial search spaces. It can also work also for other algorithms, for other search spaces. We have a very strong analogy with Euclidean spaces. So, in Euclidean spaces, you have real vectors that are both points of the space and displacements between points. The same is true in a combinatorial spaces using this framework. We made a differential mutation, a differential evolution. We have new state-of-the-art results on this problem. We have also a randomized bubble sort that can also work on generic arrays with the same worst-case complexity of the classical one. And we are doing also some work, ongoing work in red, future work in black. We have applied also to the make-span objective, and we have good results also there. We have applied also to multi-objective permutation flowshop, and we are now trying to apply to non-permutation flowshop problem, that is to release the constraint of job passing. So you have different permutation on every machine. This is very simple for us because you can exploit the product group. You consider the Cartesian products of more group, they are again a group. So we have also applying it to other permutation-based problems like the linear ordering problem. We are considering other generating set, not only adjacent swap, but also generic swap, generic change, insertion or shift of items. We are applying the same also with the scale factor parameter greater than 1, not simply truncate the shortest path, but also extend the shortest path. And we are now able also to apply it to acyclic graphs. And finally, we hope to find some theoretical aspects. We also have a bit of this. And that's all. But I think I'm the only Italian here.
So there was some work in the planning community on finding the generators for the symmetry group of a planning problem, and that allows us to do pruning of symmetric states.
Can you give me the reference?
Yes, I'll give you the reference. So that might be something you'd be interested in looking at, and maybe you can discover something new there.
Yeah, thank you.
Yeah, there's also similar work in the constraint programming community for using group theory for symmetries related to the planning stuff. So my question is, so have other people looked at genetic algorithm search spaces from this group theory perspective? Or are you the first ones to do this?
No, to my understanding, this is the first one.
So this would seem to bring you an awful lot of power beyond scheduling, beyond this particular differential evolution, right? This seems like a very powerful set of tools for genetic algorithms in general. Can you comment on that?
Yeah, I think my main purpose is to derive some theoretical results from this framework to apply to general evolutionary or also algorithms that navigate in the search space, in the solution space.
Because an awful lot of the genetic algorithm literature is very empirical, and you come up with your representation for your problem, and it works or it doesn't. So I think this is a very promising direction.
We have also some fast results about the convexity of the search space using the group theory behind.
Any other questions? All right, thank you.
Thank you.